Picture something with me, eyes closed if you can. Two black holes, far out in the dark, falling toward each other, whipping around faster than the eye can follow, so close they almost touch, dragging the shape of space with them like two spoons stirring one cup. And then they merge, and for a fraction of a heartbeat, that collision shakes the fabric of space harder than every star in the visible universe shining at once. A silent shudder races outward at the speed of light, across galaxies and through us, unfelt, until one September morning it reaches a machine built by people who believed it could be felt, and two sets of mirrors, a continent apart, tremble by the smallest amount anything has ever been measured to move. And for the first time in the history of our species, we heard it.
And I get chills every time, because the thing to hold on to is that it's not a metaphor. That shudder is real, physical, carrying energy, arriving on a specific morning at a specific instrument. We didn't see a flash of light. We felt space itself go out of shape and snap back. A brand new sense, switched on for the first time.
Okay, I'm already vibrating a little, but I also have about 9 questions. And the first is the annoyed undergrad one. Everyone says ripples in the fabric of space-time, and it sounds like a poem, and I don't actually know what it means. Can we start from something I've actually done on a homework set?
That's exactly where I want to start. Because the thing I love about this whole story is that you're closer to it than you think. You've done the homework that gets you most of the way here. One honest step from your E&M homework. So let me ask you, in your electricity and magnetism course, what does an accelerating charge do?
An accelerating charge radiates. It throws off electromagnetic waves. That's the whole back half of the course. You wiggle a charge and it sends out light, radio waves, whatever, spreading at the speed of light and carrying energy away.
Right. A charge sitting still has a boring static field. Move it at constant velocity, still boring. But accelerated, shake it back and forth, and the field can't quite keep up. Kinks form in the field lines and race outward. That's radiation. That's an antenna. That's your phone.
So where's this going? You're going to tell me mass does the same thing.
I'm going to tell you mass does something that rhymes with it. Here's the one other thing you already have. You've heard the phrase, everybody has, mass curves space-time.
Sure, heavy thing sits in space, space bends around it, and that bending is what we feel as gravity, the bowling ball on the trampoline, which I've been told 100 times is a bad picture, so I'm suspicious of it.
You're right to be, and we'll poke at it. But hold the core. A mass shapes the geometry around it the way a charge shapes the electric field around it. Now, one honest step. If an accelerating charge makes ripples in the electromagnetic field, then an accelerating mass should make ripples in the curvature of space-time. Ripples in gravity itself, spreading at the speed of light, carrying energy away. That is a gravitational wave. That's the whole idea. Everything else tonight is detail.
Wait, so this is just the accelerating charge radiate story from E&M, isn't it? Same shape of argument. You've swapped charge making an electric field for mass making the curvature of space. That feels almost too easy. That feels like something I could have guessed.
And people did guess it. Einstein wrote this down in 1916, about a year after general relativity, doing more or less the reasoning you just did. So your instinct is a century old and correct. But here's where I have to be an honest guide instead of a hype man. A real analogy is a bridge, and bridges have places where they end. Let me show you two, because those two places are secretly the whole reason this was so hard to detect.
Good, because too easy is always hiding something. Give me the fine print.
Fine print 1. In E&M, the loudest kind of radiation is dipole radiation. A positive and a negative charge wiggling apart and together. That's an antenna, fantastically efficient. Now try it with mass. Problem: there's no negative mass, and the mass version of dipole radiation turns out to be flatly forbidden by conservation of momentum. The math just gives you zero.
Why does conservation kill it? Give me the intuition, not the tensor.
Dipole radiation, for charge, comes from the average position of charge sloshing back and forth. The mass equivalent is the center of mass, and the center of mass of an isolated system can't slosh on its own. Push part one way, the rest recoils the other, and the center of mass just sits there. Momentum conservation. So the channel that's loudest for charges is switched off for mass. Nature said no.
So you can't build a gravitational antenna out of one mass going back and forth.
You cannot. So the lowest allowed kind of gravitational radiation is the next one up. Quadrupole radiation. And that sounds like jargon, so let me unjargon it. Dipole is about position, where the stuff is. Quadrupole is about shape, how lopsided and stretched out the stuff is, and whether that shape is churning.
So I don't need something that moves, I need something that changes its shape, like squishing.
Like squishing, or like two things orbiting. Picture two stars circling each other and squint at the pair as one blob. Side to side, the blob is wide and flat. A quarter orbit later, they're lined up toward you and away, and it's long and skinny. Wide, then long, then wide. The shape churns twice per orbit, a changing quadrupole. And that is what radiates gravitational waves.
Oh, that's why it's always two black holes, or two neutron stars. It's never one lonely thing. You need a pair because you need a shape that keeps rearranging itself.
You just found the deepest reason these waves were so hard to detect. Quadrupole radiation is intrinsically far weaker than dipole would be, and gravity is an absurdly feeble force to begin with. A little fridge magnet, a few grams, lifts a paperclip against the pull of the entire Earth. So you've got the weakest force in nature radiating through its weakest allowed channel. That's why you can't do this with two masses on a lab bench. You need two black holes, dozens of suns each, slamming together at nearly the speed of light to make something we can just barely hear.
That reframes everything. They're so weak that only the most violent events imaginable make ones we can detect. Can I flag one more piece of jargon?
Please, flag everything. That's your job.
You hinted the polarization is different from light, and I've heard spin 2 for gravity versus spin 1 for light thrown around. What do I do with that?
Take it only as a flavor. The real story lives in graduate field theory. A light wave pushes one way, then the opposite. That points in a direction character is spin 1. A gravitational wave doesn't push in a direction. It stretches and squeezes along two perpendicular axes at once. That's the spin 2 flavor. Light points. Gravity stretches and squeezes. Don't derive it tonight.
Deal. And stretches and squeezes along two perpendicular directions. That's setting up the detector, isn't it? If that's what the wave does, the machine has to be shaped to catch a stretch one way and a squeeze the other.
You're running ahead of me, and you're exactly right. But first, let me pay off the trampoline, because it has a limit too. The bowling ball on the rubber sheet makes it sound like there's stuff the ball dents. There is no stuff. When we say space ripples, we mean the geometry ripples. The actual answers to how far apart are these two mirrors and how long does light take to cross start oscillating. Nothing material is waving. Distance itself is waving. Keep that. Drop the rubber sheet.
Distance itself is waving. That's a genuinely weird sentence, and I need you to make it concrete, because right now I can't picture measuring it.
Then let's build the machine. The L that listens. A gravitational wave comes at you, say straight down through the ceiling and out the floor. As it passes, here's exactly what it does. It stretches distances along, say, the east-west direction, while at the same moment squeezing distances along north-south. Then it swaps. East-west squeezes, north-south stretches. Back and forth in rhythm as the wave rolls through.
And this is the distance itself is waving thing, not a wind blowing my furniture around. The actual distance from one wall to the other gets a hair longer, while the distance to the other two walls gets a hair shorter.
Exactly. And notice the gift the wave just handed us. It doesn't stretch everything the same way. That we could never catch because there'd be nothing to compare against. It stretches one direction and squeezes the perpendicular one. It's differential. So the machine is obvious once you see it. Two rulers at right angles. When one lengthens, the other shortens, and you watch the difference.
An L. You want a giant letter L.
A giant letter L, and that's literally what it is. Two arms at a right angle, meeting at a corner. In the real machines, each arm is 4 kilometers long, about 2.5 miles, in a vacuum better than outer space. Hang a mirror at the far end of each arm, and a half-silvered mirror, a beam splitter, at the corner.
And now you shine a laser at the corner.
You shine one laser beam at the beam splitter. Half the light goes down the east arm, half down the north arm. Each half races to the mirror at the end, bounces straight back to the corner, and the two beams recombine. Now, you did this in your waves course. When two beams of the same laser overlap, what happens depends on whether their ripples line up.
Interference. Crests on crests, they add. Bright. Crests on troughs, they cancel. Dark.
And here's the beautiful setup. You tune it so that when the arms are exactly equal, the two beams come back exactly out of step. Crest meets trough, and cancel. The output is dark. The detector sees nothing. The machine, at rest, is set to darkness.
That's a weird choice. Why set it up so that when everything's fine, you see nothing?
Because now nothing is the most sensitive state you can be in. You're sitting on perfect darkness. The instant one arm gets a touch longer than the other, the instant the wave stretches east and squeezes north, the beams no longer perfectly cancel, and a flicker of light leaks through. Darkness, then a whisper of light, then darkness. That photo detector reading the flicker is, in the most direct sense, reading the gravitational wave.
Oh, that's clever. A flicker out of pure darkness is far easier to catch than a change in something already bright. Like hearing a pin drop in a silent room, not at a rock concert.
Perfect. You've engineered silence so the faintest sound stands out. Ready for the number that made me want to do this for a living?
I've been braced this whole time. Go.
When a real wave from real black holes passes, how much does that 4-kilometer arm actually change in length? By about 1/1000th of the width of a single proton.
I'm sorry, 1,000th of the width of a proton. Not an atom, a proton. The thing inside the atom.
The thing inside the nucleus inside the atom. A proton is already 100,000 times smaller than an atom, and we're measuring 1,000th of that, over 4 kilometers. It is, by a wide margin, the most precise measurement human beings have ever made of anything. When people call these the most precise rulers ever built, that's the literal fact.
How is that not impossible? At that scale, everything is noise. A truck goes by, someone slams a door, the ground has tides.
All true, and fighting it is most of what the last 40 years of this field were. Heroic engineering against everything from earthquakes on the far side of the planet to the quantum jitter of the laser itself. They got it quiet enough. And how you tell a real signal from a leftover shiver of noise is exactly why you can't do this with one L.
Right, if it's one detector and it twitches, how would you ever know that twitch was two black holes a billion light years away and not a garbage truck in the parking lot?
You wouldn't. One detector twitches for 1,000 boring local reasons, So you build a second identical L far away. The two real ones are in Louisiana and in Washington state, most of the way across the country from each other. A truck in Louisiana doesn't shake a mirror in Washington, but a real wave sweeping through the Earth at the speed of light hits both. Within the light travel time between them, only about 7/1000ths of a second. So the rule is, only if both detectors see the same wiggle inside that tiny window is it real. Coincidence is the filter.
And I bet the delay does double duty. If the wave hits Louisiana first and Washington a few thousandths of a second later, that lag tells you roughly which direction it came from, like how your two ears place a sound, because it reaches one a hair before the other.
Precisely your ears. And that's why the network grew. It's not just the two American detectors now. There's a third, Virgo, near Pisa in Italy, and a fourth, Kagra, built underground in Japan. 3 or 4, spread across the planet, let you actually triangulate, pin a point on the sky and say, "Look there with your telescopes." Hold on to that. It's the hinge of the best story tonight.
Noted, but you've dodged me on one thing and I have to call it. You keep saying the arm gets longer, the space stretches. If space itself stretches, doesn't the light stretch with it? The beam is in that same stretching space. It's like measuring a table with a rubber ruler that stretches exactly as much as the table. Shouldn't it cancel and leave you with nothing?
That is the single best question in this whole subject. Asking it unprompted means you're thinking like a physicist. Here's the honest physical answer, and I'll be upfront that the fully rigorous version needs more care than we'll do out loud. Light is not a rigid ruler you lay down once. It's produced continuously by the laser, and the laser's frequency, how many crests it makes each second, is pinned by atomic physics. A clock the passing wave doesn't touch. So think of light travel time, not a static ruler. When the east arm is momentarily stretched, the light down it and back takes a little longer for the round trip. When the north arm is squeezed, its light takes a little less. The two beams come back out of step, not because you compared two rulers, but because you compared two travel times against the steady tick of the laser. That difference survives, and it leaks the flicker. The ruler stretches too, so it cancels, is exactly the trap. The way out is to measure time and keep a clock the wave can't touch.
So it's really a race between two beams, and the race has a real winner even though space is misbehaving. And the airtight version is subtler than that.
Subtler, and I won't pretend otherwise on a public show. But that picture is honest, physical, and the one working physicists carry.
Okay, so we've got the L, the darkness, the flicker, two detectors. What does the signal actually look like? Just one blip?
It is not. And its shape is the most gorgeous part. It's called the chirp. The chirp. Back to our two black holes. They radiate gravitational waves, and those waves carry away energy. So where does that energy come from? It comes out of the orbit.
Oh, the orbit is paying for the radiation. If they're bleeding energy, they can't stay in the same orbit. They fall in closer.
They fall closer. And here's the runaway, and it's beautifully counterintuitive if you remember orbital mechanics. Closer means faster. A planet near the sun whips around quicker than a far one. So they spiral in, they speed up, and the faster and closer they orbit, the harder they radiate, which drops them closer still, which speeds them up more. A feedback loop that feeds on itself and runs away toward the end.
So it's not a steady tone. The orbit keeps speeding up, so the wave's frequency keeps climbing.
The frequency climbs because it tracks how fast they go around. And the amplitude, the loudness, swells too because they're closer and heavier hitting. So you get a signal that rises in pitch and rises in volume faster and higher in the last fraction of a second, right up to the instant the two black holes touch and merge. Then it stops. The new single black hole wobbles a moment like a struck bell settling, and goes quiet.
Rising pitch, getting faster, getting louder. That's a chirp. That's what a bird does. That upward whoop.
That's exactly why they call it the chirp, and it's where this episode gets its name. For black holes this size, these frequencies happen to land right in the range of human hearing. So take the wiggle the detector recorded and pipe it straight into a speaker. No fancy translation, just play the signal as sound, and you hear a soft, rising whoop. Two black holes, more than 1 billion light-years away, and the last flicker of their death spiral comes out of a laptop speaker as a rising whistle. People have heard it. It's public.
I have to flag the word listening, though, since the whole thing's called listening to space-time. That's not really sound, is it? There's no air out there. The black holes didn't make a noise that travelled to us.
Thank you. Analogy police doing good work. No, nothing travelled through air. There are no pressure waves. What the detector measured is space-time strain, that stretching and squeezing of distance, and because those wiggles fall in the same range as audible sound, we translate them into something your ear can process. Listening is a metaphor for a completely new sense. For 400 years, astronomy meant catching light, always light. This is the first time we've sensed the cosmos through something that is not light at all. A new sense is right. Hearing sound from space is wrong.
A new sense. Okay, so we've built the thing and we understand the chirp. When did it pay off? When did someone see the flicker for real?
September 2015, and that morning's story is even better than you'd hope. The first detection. The detectors had just been through a major upgrade, brand new sensitivity, and were in final engineering checks, not even officially switched on for the science run. And a signal comes through both, Louisiana first, Washington about 7/1000ths of a second later, right in the coincidence window. A clean chirp, rising pitch, rising volume, a peak, a ring down. Almost too textbook.
So good, it's suspicious. I'd assume glitch, or a test someone snuck in.
That's what half of them assumed. There was a system where a few people could secretly inject fake signals to keep everyone honest. So the first reaction of many physicists was, all right, who did this? It took weeks to establish that no, the injection system wasn't even armed. This was the sky.
So what made that whoop?
Two black holes, one about 36 times the mass of our Sun, the other about 29. They merged into a single black hole of about 62 solar masses.
Hang on, undergrads love a conservation law. 36 plus 29 is 65, but the final one is 62. 3 solar masses are just missing. Where did 3 entire suns worth of mass go?
You just found the energy source. That missing 3 solar masses is exactly what was radiated away as gravitational waves. 3 times the whole mass of the Sun, converted through E equals mc squared into rippling spacetime in about 0.2 of 1 second.
3 suns, turned into pure gravitational waves. In 0.2 of a second.
And now I can give you the line from the very start, carefully, because it gets mangled. For that fraction of a second, at the peak of the merger, the power radiated in gravitational waves, the energy per second, was greater than the combined light of every star in the observable universe. All of them at once.
That can't be right. That's exactly what you told me to be suspicious of.
And you should be. So let me fence it precisely. The honest version is more impressive than the sloppy one. It's not more total energy than all the stars ever emit. It's not visible light. The black holes are dark. You couldn't have seen this at all. It's specifically peak power, energy per second, in gravitational waves, for 1 instant of maybe 0.2 of a second. In that instant, that one collision outshone the whole universe, but in a shining your eyes can't see, and only for the blink of the merger. Any looser and you're overselling.
The real fact is wilder than the exaggeration. You just have to be exact about which fact it is. How far away were they?
About 1.3 billion light-years. So that chirp had been racing across the universe for roughly 1.3 billion years before it reached Louisiana. When those waves set out, the most complicated life on Earth was single cells, and the machine was ready by a margin of days.
A signal 1 billion+ years in flight, and we finished the antenna the week before. So this is it, the first direct detection of a gravitational wave.
First direct detection announced in February of 2016. It confirmed something Einstein predicted a century earlier and doubted could ever be measured, and gave us the first direct proof that pairs of black holes exist and merge. 2 years later, in 2017, the Nobel Prize in Physics went to 3 people most responsible. Rainer Weiss took 1/2 for working out more than anyone how you'd actually build such a thing. Barry Barish and Kip Thorne shared the other for turning it into the vast collaboration that pulled it off.
So we detected black holes, famously dark. Which raises the obvious question, if the thing that merges does give off light, do we get to point telescopes at it?
Now you've asked the question that opens the best door in modern astronomy. And the answer arrived almost exactly 2 years later. 2 neutron stars and a new kind of astronomy. August 2017. By now the detectors are better, and the Italian one, Virgo, is online too. 3 L's on the planet. And a signal comes in, but different from the first. Big, heavy black holes merge in a fraction of a second. This one lasted far longer. A long, patient rising whistle.
Longer means lighter, right? A long, slow chirp has to be something less massive, spiraling in more gradually.
Exactly. The masses came out to something like 1 1/3 to 1.5 times the Sun each, the calling card of a neutron star. 2 neutron stars, the collapsed cores of dead giant stars, each heavier than the Sun, but squeezed to the size of a city, so dense a sugar cube of them would weigh as much as a mountain.
And neutron stars are made of matter. They're not black, so this time there should be light. Fireworks.
This time there should be light, and here 3 detectors earn their keep. With Louisiana, Washington, and Italy all catching the wave, the team could triangulate, pin it to a patch of sky, and flash that patch to observatories worldwide. Point everything you've got right here. And here's what still gives me chills. About 1.7 seconds after the wave ended, a space telescope watching for gamma rays caught a short burst from the same direction, a flash of the highest energy light there is.
1.7 seconds. And how far away was this one?
About 130 million light-years in a galaxy catalogued as NGC 4993. Much closer than the first black holes, which is part of why it was so bright and so well located.
So the gravitational wave and the gamma ray flash both crossed 130 million light-years and arrived within 1.7 seconds of each other. They raced 130 million years of space and finished neck and neck.
That's why physicists lost their minds. 2 messengers, a ripple in space-time and a beam of light, from the same catastrophe, crossing the line 1.7 seconds apart. A gorgeous confirmation that gravitational waves and light travel at the same speed to fantastic precision. Exactly what Einstein's theory demands. And it was the first time in history we caught the same event in gravitational waves and in light. 2 different senses aimed at one explosion.
And that's the phrase, multi-messenger astronomy. Gravity is one messenger, light is the other.
That's the whole idea, and that night is its birthday. And it didn't stop at gamma rays. As telescopes swung to that galaxy over the following days, they caught a new point of light that hadn't been there, glowing, then fading, then reddening. A kind of explosion astronomers had suspected but never confirmed. a kilonova. And the kilonova is where this comes home to you personally.
To me personally? How did two neutron stars 130 million light-years away get personal?
Because of what that glow was made of. When two neutron stars shred each other, they fling out a spray of incredibly neutron-rich matter. And in that hot, dense debris, atomic nuclei go on a building spree, capturing neutrons fast, one after another, climbing the periodic table into the heaviest elements there are. Gold, platinum. The fading, reddening glow of the kilonova is the light of exactly that freshly forged heavy matter, radioactively cooking off. We watched a cosmic factory for gold switch on, live.
Wait, so the gold in a wedding ring, that gold?
A good fraction of the gold and platinum in the universe, the stuff in the ring, in the phone in your pocket, we now have direct evidence is forged in collisions like this. Not in ordinary stars, in the merger of dead ones. And let me be careful. I won't quote you a precise number of Earth masses of gold from that one event. Those estimates carry real uncertainty, and I won't fake a precision we don't have. But qualitatively, that neutron-star mergers are a major cosmic forge for the heaviest elements. That's what this event nailed down for the first time. The heavy stuff in your body has a violent birthplace, and in 2017, we finally watched it happen.
Okay, we can hear black holes, hear and see neutron stars, watch gold get made. What don't we know? You've been good all night about where the bridges end. I want the honest edge.
And let me take you right to it. Because the edge is where you come in. The honest horizon. 3 open frontiers, and for each I'll tell you what's solid and what's still up in the air. The first is maybe the biggest embarrassment in cosmology right now, the Hubble tension.
Hubble as in the expanding universe. Distant galaxies flying away, and the farther they are, the faster they go.
That one. There's a number for how fast, how much more quickly a galaxy recedes for each extra chunk of distance. Call it the expansion rate. 2 well-established ways to measure it. One reads the early universe, the ancient afterglow of the Big Bang, the cosmic microwave background, and works forward. The other reads the nearby universe, measuring distances to close galaxies with a chain of known light sources. 2 careful methods, and they disagree.
How badly? In a lab, 2 measurements never land exactly on top of each other. Maybe the error bars overlap, and everyone needs to calm down.
Right instinct. First thing everyone checked, for years. But no, the early universe method gives a number around 67. The local method around 73. And both are now so precise that the gap is about 5 sigma. And in your statistics course, 5 sigma is the threshold for declaring a discovery, a 1 in a few million chance it's a fluke. 2 extremely sharp numbers that flatly refuse to agree. And under scrutiny, the tension has, if anything, gotten firmer.
So either there's a subtle systematic nobody's found, or the universe is doing something our theory doesn't include. New physics.
Exactly those 2, and nobody knows which. A live, unresolved puzzle, not a settled story. And here's where gravitational waves walk on as a referee. You know the standard candle idea. If you know a light source's true brightness, how dim it looks gives its distance. A ladder of known light sources. A gravitational wave merger gives you something independent. The shape of the chirp, matched to theory, tells you the source's true loudness at merger. So how faint the wave arrives gives the absolute distance directly, without that ladder at all. People call it a standard siren, to rhyme with standard candle.
Oh, clever. So the neutron-star merger, where you also caught the light and knew the exact galaxy, you get distance from the gravitational wave, the galaxy's light gives how fast it's receding, and you combine them for the expansion rate. A separate third method that doesn't lean on the other two.
You just designed the measurement. That's what they did with the 2017 merger. And here I hold the honesty line hard, because it's so easy to oversell. That first siren number came out around 70, but with error bars wide enough to agree with both camps at once. So it did not resolve the tension, it didn't crown a winner. What it did was prove a genuinely independent referee exists, a third ruler that sidesteps the light ladder argument entirely. And the hoped-for part, not the done part, is that with enough future mergers, that referee gets sharp enough to settle which side is right, or show the theory itself must change. An open question a student your age could be the one to close.
I like that you keep separating those. This is proved, this is hoped. It makes the hoped part more exciting, not less, because I know you're not blowing smoke. Second frontier?
What is a neutron star actually made of? It crushes more than a sun's worth of matter into the size of a city. The densest stuff in the universe, short of a black hole, denser than an atomic nucleus. And we don't know the rules matter obeys down there. Does it stay neutrons packed shoulder to shoulder? Do they dissolve into their quarks, some exotic quark soup? We genuinely don't know. Physicists call the missing rulebook the equation of state, one of the big open problems where nuclear physics meets astrophysics.
And let me guess, the merger helps, because in the last moments the two stars are squeezing each other. Tides, like the moon on Earth, but monstrous.
Exactly. Each star's gravity stretches the other, raises tides, and how much it deforms depends on how stiff or squishy that ultra-dense matter is. A stiffer star deforms less, a softer one more, and that leaves a faint fingerprint on the very end of the chirp. So the 2017 merger gave us the first real observational handle on it. Honest scorecard, it constrained the possibilities, disfavored the stiffest models, told us neutron stars can't be quite as large and puffy as some theories allowed. But it did not tell us what the stuff is. It narrowed the menu, it didn't name the dish. Whether there are free quarks in the core is still wide open. First real handle, not solved.
Constrained, not solved. And the third frontier? You said the black holes we hear sit in the range of human hearing, which makes me think there are notes above and below that we're deaf to.
Exactly the right picture, and a lovely place to end. Everything tonight lives in one band. The band those 4-kilometer Ls on the ground are tuned to, which happens to be roughly audio range. But the universe rings at other frequencies too, and we're just now building new ears. Down at the very lowest frequencies, waves so slow a single up and down might take years, there's a completely different technique. Instead of building an instrument, you use the galaxy itself.
How do you use the galaxy as a detector?
Pulsars. A spinning neutron star sweeps a beam of radio waves past us like a lighthouse, ticking with the regularity of an atomic clock. Watch dozens of these natural clocks across the sky for years, and if a gravitational wave with a years-long wavelength rolls through the galaxy, it slightly stretches and squeezes the distances to those pulsars. So their ticks arrive a hair early here, a hair late there, in a pattern correlated across the whole sky. And in 2023, a collaboration called NanoGrav, with partner teams around the world, reported evidence for exactly that. A low, galaxy-spanning hum in this ultra-low frequency band.
The detector is a patch of the galaxy hundreds of light years across, and I noticed you said evidence for, not discovered.
Deliberately, that's the honest word. It's not yet at the 5 sigma nail-in-the-coffin level the first black hole chirp was. It's strong, suggestive evidence, and several independent pulsar timing teams saw a consistent signal the same season. Encouraging. The leading explanation is enormous pairs of supermassive black holes, the monsters at galactic centers slowly circling after their galaxies merged. but exotic sources from the early universe can't be ruled out yet. Exciting, real, still being nailed down. And notice a completely different frequency window from the ground detectors. A different octave of the universe entirely.
A different octave. So we've got the audio range window on the ground and this ultra-slow window off the pulsars. Anything in between?
A whole middle range the ground can't reach, because on the ground, the shivering of the Earth itself drowns those frequencies out. So the plan is to leave the Earth. There's a mission called LISA, a gravitational-wave detector in space. Same core idea, laser beams, arm length, watch the timing. But instead of 4 kilometers in a tunnel, it's 3 spacecraft in a triangle, trailing the Earth around the Sun, with arms about 2.5 million kilometers long.
2.5 million kilometers instead of 4. That's not an upgrade. That's a different scale of ambition entirely.
A different regime. And let me be careful with the tense. Real but not flying yet. The mission has been formally adopted by the European Space Agency, approved, being built, with launch planned for around the mid-2030s. A genuine plan with real hardware behind it, not a fantasy, but it hasn't launched, and space schedules move. When it flies, it'll open the frequencies where the truly giant black hole mergers ring. The million-sun and billion-sun monsters the ground detectors simply cannot hear.
Let me try to say the whole horizon back to you. Honestly, the way you've modelled it, we've proved gravitational waves are real. The ground detectors have catalogued a few hundred now, so that's just true. We've proved neutron-star mergers forge heavy elements. Also just true. But we have not resolved why the 2 measurements of the expansion disagree, though the standard siren is a real independent referee that might one day settle it. We have not figured out what neutron-star cores are made of, though the merger narrowed it down. And we're only just opening the other windows. The pulsar hum is evidence, not yet a lock, and the space detector is approved but hasn't flown.
A flawless summary, and holding the proved and the hoped in 2 separate hands is the entire point of doing it this way. So here's what I want you to walk out with. Every one of those open questions was, not long ago, considered permanently out of reach. Einstein himself doubted we'd ever measure a gravitational wave. He thought it too faint to catch. And people your age, sitting where you're sitting, built the machine that caught it anyway. The frontier isn't some far country reserved for geniuses. It's one honest step past the homework you did this week. An accelerating charge radiates. You knew that. An accelerating mass radiates too. Now you know that. Everything after it is just the same courage, one more step out.
One honest step past the homework. That might be my favourite thing anyone said to me about physics. Thank you. Genuinely. I came in thinking Ripples in Spacetime was a poem, and I'm leaving able to nearly build the detector in my head.
You could build it in your head. That's the whole point. Go listen to the chirp, the real ones out there. A soft, rising whistle from 2 black holes that died before the Earth was born. Then go do your next problem set, knowing the frontier is closer than they told you.
I will. Until next time, keep listening to the universe. It's talking, and we're finally learning how to hear it.